All right, everyone, we are back, and we're going to do our last problem on our exam, creep, creep, creep. Let's look at the deformation mechanism maps. Let's label the sections. So I'm just going to do it for one because you know the answers. Theoretical stress, elastic, dislocation glide. This is going to be our NH. This little region is going to be our CC. This will be PLC. And you see it's pretty similar for the rest of these maps. So rank the yield stress of these maps. So we see that my sigma y of B is greater than my sigma y of A, which is greater than my sigma y of C. Rank the yield, the grain size of each map. Well, the Coble creep region is changing, so I'm going to say the grain size for all these are equal. There we go. What strengthening mechanisms can produce these curves? Well, because the Coble creep region isn't changing, but my yield stress is, it could be precipitate, or it could be solute strengthening, where it's sigma y scales as C solute to the 1/2 power. Produce these mechanisms. Draw the stress strain curves that correlate. So if I were to draw stress and strain, so there might be slightly different. So for example, like this. So I'm drawing these probably a little bit more exaggerated, but this would be B, A, and C. So the Young's modulus is changing, my yield stress obviously is changing as well, and my ductility changes. Fantastic. Whoops. This looks like the wrong little question here. Looks like I did not. Did I not? Unfortunately, grain size. Okay, C, this is incorrect here. So the question on our exam is, I'm going to take the map from material C, and then I'm going to reduce the grain size. How will the map change? How will the stress strain curve change? So if I reduce the grain size, this line will go up, this region will get much larger. And if I grain size strengthen this, it's going to be the same Young's modulus, but higher yield stress and then fractures earlier. And then finally, the last question is, why does Nabarro herring dominate at higher temperatures than CC? Justify with any equations, pictures, and graphs. So we know that our strain of NH is equal to K NH stress dg to the -3. And then it's also d naught exponential minus q grain boundary over kt. Our, -2, and then this is lattice. Our Coble is K Coble stress dg to the -3, d naught exponential minus q gb over kt. So when I have a material that has small grain size, I have more pathways to diffuse along the grain boundary. And this diffusive term is always greater than this diffusive term here because our activation energy for grain boundary diffusion is less than that for the lattice. Now, at high enough temperatures, even when I have a material like this where I'm moving way faster along the grain boundaries, the motion of the particles in the bulk will overcome and lead to that kind of strain value here. So obviously I want to have a lot more discussion and I want to see what you do, but that's essentially the gist of this problem. So see you next time. Thanks. Bye.